Let's look at vertical and horizontal asymptotes. So in this example 1, we had 1 over x. And so in this example, the behavior of f near x equals 0 is the y values approach negative infinity as x approaches 0 from the left side. And then from the right side, the y values approach positive infinity as x approaches 0 from the right side. The line x equals 0 is a vertical asymptote of the graph. And then so it also has a horizontal asymptote at y equals 0. So another thing, let's talk about the behavior of f near y equals 0. So f of x approaches 0. It's approaching 0 as x approaches negative infinity, right? So it's going towards that 0 here on this side. Then f of x approaches 0 as x approaches infinity on the right side, right? It's getting closer and closer to that asymptote. So definitions of vertical and horizontal asymptotes. The line x equals a is a vertical asymptote of the graph, and then the line y equals b is a horizontal asymptote of the graph. But let's look at when do we know that. So this is our function, our rational function here. So n of x is our numerator function, and then the d of x is our denominator polynomial, and then they have no common factors. The graph of f has vertical asymptotes at the zeros of the denominator. So we know that. We remember from last year. But this year, we're focusing on some horizontal asymptotes in pre-cal. So the graph of f has at most one horizontal asymptote determined by comparing the degrees of n of x and d of x. So we're comparing the numerator, the degrees of the numerator and the denominator. When n is less than m, the graph of f has a line y equals 0, the x-axis, as a horizontal asymptote. So one that I keep in my mind is 1 over x. So thinking when we graph that, we know that we have a horizontal asymptote there. Another example we can think of is maybe like x over x squared. So notice that the degree is only 1 at the top and 2 at the bottom, right? So n is less than m. And so that is when the horizontal asymptote is y equals 0. Then when n equals m, so if we have like 3x over 2x, then it's the ratio of the leading coefficients. So it's 3 over 2 in this case. If we take a look at this example here that we did earlier, 3x over x minus 1, if you were to graph it, you would realize that the horizontal asymptote is at 3. It's 3x over x, so it's just the leading coefficient of 3 to help us out. Then the last one is when n is greater than m. The graph of f actually has no horizontal asymptotes. So for example, if we have x cubed over x squared, then we have no horizontal asymptote. So we're going to focus mainly on A and B for now, and then we'll get to practicing some graphing. Example 2, finding vertical and horizontal asymptotes. Find all vertical and horizontal asymptotes of the graph of each rational function. So letter A, we know that the degrees are equal, 2x squared over x squared. So in this case, our horizontal asymptote is going to be the leading coefficients of the polynomials of the numerator and denominator. So the horizontal asymptote is at 2, or actually more specifically, it should be y equals 2. It's a horizontal line. Then in order to figure out the vertical asymptotes, we need to find the zeros of the denominator. So this is x minus 1, x plus 1. So we know that we have vertical asymptotes at those zeros. And so that's going to be at x equals 1 and x equals negative 1. Now just to kind of graph it, just to get a visual of what this looks like, we have a horizontal asymptote at y equals 2. So it would be this. Then our vertical asymptotes would be at 1 and negative 1. And then so it would look like this. Okay. Letter B. So we know that the degrees are the same. So we know we have a horizontal asymptote at y equals 1. Then let's factor this, because we can factor the numerator and denominator. So this factors to x plus 2 times x minus 1. The denominator factors to x plus 2 times x minus 3. So we can cancel out x plus 2. And so in this case, this is actually not a vertical asymptote, but it is a restriction. So remember that we know that it's all real numbers, x, except x cannot equal negative 2, so x equals 2 and x equals 3. Now what happens at this x equals 2, that's actually a hole at the negative 2. So to just finish this one out for sure, let's talk about our vertical asymptote. So our only vertical asymptote is actually only at x equals 3. Then, just as a note for the negative 2, that is a hole. So there's a hole at x equals negative 2. So if we were to graph it, I don't know what this graph looks like right now, but if we have a graph here and say, for instance, let's see, vertical asymptote is at 3, horizontal asymptote is at 1, then maybe the graph does something like this. At x equals negative 2, let's just say it's here, that would be a hole at that point, but it's not a vertical asymptote. It just means it's undefined only at that spot. So go ahead and try this example here. Find all vertical and horizontal asymptotes of this graph, and then maybe just tell me there was a hole at a certain spot if there is one. So pause the video, and when you come back, I'll have the answer for you. So if you try this out, you would have a horizontal asymptote at y equals 3 because the degrees are the same, so it's just the leading coefficient, y equals 3. Then when you factor the numerator and denominator, you notice that x plus 3 cancels. And so our only vertical asymptote is x equals negative 1. And then we have a hole at x equals negative 3. And then if you plugged in negative 3 into this equation here, you could find exactly where that hole is. That would be at 9 minus 2 over, negative 9 minus 2 over negative 3 plus 1. So that would be negative 11 over negative 2, or at 11 halves. So 11 halves, comma, negative 3, comma, 11 halves. That would be where the hole is, just as an FYI. I hope this helps. Thanks for watching.